So my talk is going to be on telescoping. And so telescoping isn't referring to that telescope, but just a style of solving certain kind of stuff. So, okay, finally Zoom is allowing me to share screen. Okay, sorry about that. So yeah, so here. So do all of you see the, okay, I'll assume all of you do. So yeah. So now I'll be just, so first of all, I should probably explain what telescoping is. So telescoping is really just, as I mentioned just now, a format of, sorry, a certain style of solving summations. And so you can use it to solve stuff like the sum of, let's see. So a normal would be something like 1 over n times n plus 1. So this is the example. Okay, hold on a second. Okay, sorry about that. Anyway, so yeah. So I'll assume that all of you can see. Anyways, so this is an example of a really basic telescoping sum. It's not, doesn't really count as one of the problems. But anyway, so the way telescoping works is that basically for summations, you're trying to get it into the form of 1 over n, or sorry, something. I'll just write SMPH for something minus something else. And you want it in a way such that the something else will cancel out with something if you repeatedly substitute in. All right, I'm aware that this is okay. So my computer is being glitchy, I guess. Anyways, so okay. Well, I don't think there's any issue with my screen share, just on my side, I guess. So so you can see that 1 over n times n plus 1 is equal to 1 over n minus 1 over n plus 1, because, well, you can't really see that this is true, but like this is true. And then so let's set n equals 1 to 10. So then, actually no, 5 is probably easier. So then this just becomes 1 over 1 minus 1/2 for n equals 1, n equals 2, 1/2 minus 1/3, 1/3 minus 1/4, 1/4 minus 1/5, and 1/5 minus 1/6. So the key idea of telescoping is basically you get that these terms cancel each other. And so then all you're left with is 1 minus 1/6, which is just 5/6. So that's basically how you do the idea of telescoping. So does everyone understand that? Ho? Any responses? I don't see any response. Okay. All right. So with that said, I'll be switching to the slide that I prepared. So new share, and so, okay, please stop glitching. Okay, please wait for a second. New share, okay, here we go. Okay, I'll now be assuming that y'all can see this. So, yeah, so as said here, my topic is telescoping. And so this is the first example. And so I'll just give a short minute, I guess, for all of you to do this problem on your own, and then I'll start explaining. Because telescoping, it's at start it might seem really contrived, and there's really no good way to give you a hint on how to do this except for saying using telescoping stuff. So yeah, telescoping, really all you can do to get fluent at it is just through sheer experience. I don't think there's really any way of like being able to see it really nicely, any trick to do that. So yeah. Okay, well, I don't know if you managed to get it or not, but regardless, I'll be starting to explain that. Okay, so the way you can do this, it's a bit contrived, but you can see that 3, okay, I guess I'm just lagging on my part. Okay, so 3, this 3k squared minus 1 over k cubed minus k cubed. So this is just equal to k minus 1/2 divided by k squared times k minus 1 squared minus k plus 1/2 divided by a similar thing. So k squared times k plus 1 squared. And so, yes, I'm aware this is pretty contrived, but yeah, it's just this way. And I'll just give you a second for you to verify this on your own. And then, so of course, you can just plug, and then so you can see that if you plug in k plus 1 into k, then what you get is that this is equal to k plus 1/2 times k plus 1 squared times k squared, which is just this. So you can see that this is just 1 minus 1/2 times 1 squared times, actually, there's a typo. This should be a 2. Sorry. Anyway, so it's 2 minus 1/2 times 2 squared times 1 squared. And so this is 3/8. And of course, this sums to n. So the minus n part has not been taken out. So it's minus n plus 1/2 times n squared times n plus 1 squared. So yeah, you can see that for telescoping problems, if you know the telescope, it's really, really simple. And if you don't, then it kind of just doesn't work out well. So yeah, with that said, here's more practice. So yeah, so now I'll give you guys another minute to try and do it on your own. Okay, well, that's the minute. So yeah. So here we have 2 to the k plus 1. Oops. 2 to the k plus 1 over 3 to the power of 2 to the k plus 1. Okay, that k might have crossed it a little, but that's fine. So now, so you can see that this is basically 2 times the exponent of this. So yeah, sorry. So yeah. So now we can just, this may seem a bit contrived, but first you can start with 1 over a plus 1 because the denominator is kind of in the form a plus 1. And so this is telescoping. So one of the first thing you can do is think of a difference of squares and how to make one. So you just multiply the numerator and denominator by a minus 1. And then you just split this apart. So this is negative 1 over a squared minus 1 plus 1/2 of the sum of a plus 1. Sorry, the sum of 1 over a plus 1 and the sum 1 over a minus 1. And so that means that 1/2 of 1 over a plus 1 is just equal to 1 over 2 times a minus 1 minus 1 over a squared minus 1. And so remember that we set a, so remember that we said that a is equal to 3 to the 2 to the 2. And so that means that 1 over 2 times 3 to the 2 to the k plus 1 is equal to half of 1 over 3 to the 2 to the k minus 1 minus 1 over 3 to the 2 to the k plus 1 minus 1. And so now what you do is multiply through everything by 2 to the k plus 2. So now what you get is that this is equal to the power of k plus 1 over 3 to the 2 to the k plus 1. And this is equal to the k plus 1. Oops. to the k plus 1 over 3 to the power of 2 to the k minus 1 minus 2 to the power of k plus 2 over 3 to the power of 2 to the k plus 1 minus 1. And so now what we can see really clearly is that if we plug in k plus 1 into k, this goes to this. So this is equal to the sum from k equals 0 to n of 2 to the k plus this thing. Okay, I won't bother to rewrite it because it's pretty close to 630 actually. Anyway, so this thing. And so now if you plug in k equals 0 to here, what you get is just 1. And of course, everything else cancels except for the minus n term. And if you plug that in here, you get 2 to the power of n plus 2 over 3 to the power of 2 to the n plus 1 minus 1. And so next is this one. And so once again, I'll give a minute to try this on your own. Okay, so that's about enough. And so now start going over this problem too. So this one is probably slightly less contrived than normal. Anyways, this one is just so sorry. So I'll just be showing you how to split this up. So you can split this into 2k plus 1 plus the square root of 2k plus 1 times 2k minus 1 plus 2k minus 1. And this is all, okay. And this is all over the square root of 2k plus 1 plus the square root of 2k minus 1. So you can see that now you can multiply numerator and denominator by this. The square root of 2k plus 1 minus the square root of 2k minus 1. Sorry, square root of 2k plus 1 minus the square root of 2k minus 1. And so the numerator forms a difference of squares. Sorry, difference of cubes, because this is a squared plus ab plus b squared, and this is a minus b. So the ending result is that this is equal to the square root of 2k plus 1 cubed minus the square root of 2k minus 1 cubed. And this is all divided by 2k plus 1 2k plus 1 minus 2k minus 1. And so this is just 1/2 of the sum from k equals 1 to m of the square root of 2k plus 1 cubed minus the square root of 2k minus 1 cubed. Anyways, so yeah, you can see that k to k plus 1 will turn one of these into the other. And so you can just see that this is just 1/2 of, and so the larger term is the one being added. Sorry. Yeah. The term with the larger stuff is the one being added. So this time it's the value of this for m minus the value of this at 1. So that would be just the square root of 2n plus 1 cubed minus 1. And of course, it's half. So next is this problem. And so this problem would need, well, one of the solutions to this problem would use something called Sophie Germain's identity, which is the fact that a to the fourth plus 4b to the fourth is equal to a squared minus 2ab plus 2b squared times a squared plus 2ab plus 2b squared. And it's basically difference of squares, but it's done on a squared plus 2b squared minus 2b squared. What? Not sure what. Okay. Anyways. Oh, sorry. 2ab squared. And yeah. So in the interest of time, I guess I'll start just going through these problems without doing much waiting. So you can use this to the denominator, and this just simplifies it to, so this is just the denominator. So I'll be using a different color. So it's 2k plus 1 squared minus 2 times 2k plus 1 plus 2 times 2k plus 1 squared plus 2 times 2k plus 1 plus 2. And so this is 4k squared plus 4k plus 1 minus 4k minus 2 plus 2 times 4k squared plus 4k plus 1 plus 4k plus 2 plus 2. And this simplifies to 4k squared plus 1 times 4k squared plus 8k plus 5. And you can see that this is actually just 4 times k plus 1 squared plus 1. So yeah, the pattern, as the usual pattern, still holds, basically. So yeah. And so next up, we're back to the whole thing. So it's 2k plus 1 cubed over 4k squared plus 1 times 4 times k plus 1 squared plus 1. And so now one of the more common ways to solve algebraically for a telescoping sum is to use this. So it's to use something like this. So of course, A, B, C, and D are all variables that you are trying to find. And then you can cross multiply and use the fact that you know the coefficients of the terms and stuff, and then you can solve. But I won't be doing that here because it's long and it's really just it's really just solving a 4x4 system of equation here, which isn't fun, no matter how you try. So yeah, so this sum is equal to the sum from k equals 0 to n of -1 to the k times, so once you solve it, you can see that a is 1, b is 0, and c is 1, and d is 1, which is a fairly nice solution, really. And so this is -1 to the k times k over 4k squared plus 1 plus k plus 1 over 4 times k plus 1 squared plus 1. And so you can do a little manipulation, and this is equal to the sum. I won't be writing this anymore because I think all of you know what I'm referring to, and so I can just abbreviate it with the sum. So this is just equal to -1 to the k times k over 4k. Okay, 4k squared, not 4 to the k. 4k squared plus 1 minus -1 to the k plus 1, because -1 squared is just 1, times k plus 1 over 4k squared plus 8k plus 5. And so this is very clearly a telescoping thing. And so you can do the usual stuff at the end, and what you'd find is that this is just equal to negative of -1 to the n plus 1 times n plus 1 over 4 times n plus 1 squared plus 1. And you can leave it like this, or you can expand. So you can also leave it like -1 to the n times n plus 1 over 4n squared plus 8n plus 5. But at this point, these two are effectively the same thing. And so next problem is this one. So okay, so how you would start finding the telescoping for this one, you can just see that this is, so we can just first multiply everything by the square root of 2. So root 2 over root 2k plus 2 times the square root of k minus 1, k plus 1. And so this is just equal to square root of 2 over the square root of k minus 1, square root of k minus 1 squared plus the square root of k plus 1 squared plus 2 times the square root of k minus 1, k plus 1. And so this denominator is in the form root k minus 1 plus root k plus 1 squared. Okay, and so this is just root 2 times sum of 1 over root k plus 1 plus root k minus 1. So next what you can do is just rationalize the denominator, which means you're multiplying it by k plus 1 minus k minus 1 over k plus root k plus 1 minus root k minus 1. And doing this, you can just get that the sum here is equal to root 2 times the sum of root k plus 1 minus root k minus 1 over 2. And so, well, this isn't completely fully normal telescoping anymore, but it's still very telescoping. So the way you can do this is just root m plus 1 minus root m minus 1, root m minus root m minus 2, root m minus 1 minus root m minus 3, and then so on to root 4 minus root 2, root 3 minus root 1, and root 2 minus root 0. So the terms that cancel out are these. Okay. So this is just root 2 over 2 times root m plus 1 plus root m minus 1. And so that's the answer to this question. And so next up, we have another one. So it's roots. Sorry. So you're saying root. Anyway, so this time it's just this. And well, honestly, factorials are probably one of the easier ones. And so this is equal to just the sum of k times k plus 2 minus k plus 1. Okay, I don't know what I was writing here, but k times k plus 2 minus this over k plus 2 factorial. And so that means that this is just the sum of k over k plus 1 factorial. Okay, sorry. I might have done it a bit too late. But anyways, okay, leaving that aside. So this is k over k plus 1 factorial. And then it's minus k plus 1 over k plus 2 factorial. And you can see that plugging one of these in results in the plugging k plus 1 into k results in the other. So yeah, this is one of the easier ones, and this is equal just to 1/2 minus n plus 1 over n plus 2 factorial, because this is what happens for 1 over 1 plus 1 factorial. And so something to remember is that in general, for these kinds of sums, stuff with factorials in the denominator is probably generally on the easier side, because they usually end up doing something like this. They usually end, if of course it falls under the telescoping domain. If it doesn't, it might not be as nice. But usually factorials in telescoping problems are fairly nice. And so yeah, I just wanted to show you an example of a product here. So here is the product. So this is equal to the product from k equals to the n of k minus 1 over k plus 1 times the product of k equals 2 to n of k squared plus k plus 1 over k squared minus k plus 1. And if you notice, you can see that plugging in k plus 1 into k will get k squared minus k plus 1 to k squared plus k plus 1. And so really, this just basically all canceled out, except for a bit, and the same goes for this. So we can do these separately. So the first one is 1/3 times, let me change the color real fast. So blah. So 1/3 times 2/4 times 3/5, and so on, all the way to n minus 2 over n times n minus 1 over n plus 1. So the ones that get canceled out are all of these. So this is 2 over n times n plus 1. And here, this is 7/3 times 13 over 7 times 20 over 13, all the way to n squared plus n plus 1 over n squared minus n plus 1. And all of this cancels, so this leaves you with n squared plus n minus plus 1 over 3. And so this just means that the product is equal to 2/3 of n squared plus n plus 1 over n squared plus n. So that's how you do products. This was probably one of the nicer ones, so don't just assume that all the products are nicer than this one. And so this is the last question, and I'll just be leaving this as homework. So this is what you're trying to find. Red probably is better. So you're trying to find the sum from 1 to 4,012,008 and of this thing. So, well, yeah, so this is your homework problem. So yeah, please don't forget about it. And so, and if you want a hint, just, I guess I'll tell you guys a little hint. And I guess it would just be to especially take note of the fact that think about, I guess, why the number 4,012,008 was chosen. Although, so that's what would usually apply to problems like this, but actually, in this kind of problem, it's usually somewhat of, if you just think about the number 4,012,008, you'll probably get into a dead end. So you should start thinking about its properties in relation to other numbers, stuff nearby, and stuff like that. Yeah. And also note that these two are very much related. And so with that said, I guess that's it for my lecture as well. And so thank you for coming today. And I hope all of you can have a nice rest of your weekend. So thank you for coming, and bye.